Hi everyone. So today we'll be discussing nodal analysis, and it's a powerful tool that we'll be using to try to solve for the different currents and voltages within the circuit. So now that we have a good understanding of Ohm's law and Kirchhoff's law, we can establish new methods or analysis techniques to try to solve for the different voltages and currents within the circuit. Now, two techniques will be introduced in this circuit. One is nodal analysis, which is mainly based on Kirchhoff's current law, or KCL, and then mesh analysis, which is mainly based on KVL. Now, any linear circuit can be analyzed using these two techniques. Now, what we will end up getting after we perform these analyses is getting a set of linear equations that we need to solve. Obviously, these set of linear equations can be solved using either Cramer's rule, or you can use MATLAB or other software that can solve matrices. And we will get there and present some of these results later. So instead of focusing on the voltages of the circuit elements, we could actually look at the voltages at the nodes within the circuit. So if we look at a circuit and it has n nodes, the overall steps that we will use to try to analyze the circuit can be summarized as follows. We select one node to be the reference node. Now, you can select any node to be a reference node, obviously, but generally speaking, we select the ground node to be the reference node. Now, you may ask, what is the ground node? And that's a very good question, because that is also even determined, and we will get there in the next visual example that I will give. But basically, we will select the node that is shared amongst the most number of elements to be the ground node. And if there is a voltage source there, it can be helpful in trying to determine where would be the ground node. So we would select, nevertheless, one node to be the reference node, and then we will assign voltages V1 to Vn minus 1 to all the other nodes. Now we apply KCL at each node, so we will get n minus 1 set of equations, and then we will try to solve the simultaneous equations that we have, n minus 1 simultaneous equations, to determine all the currents within this circuit. Now, the reference node is obviously, as I mentioned before, it is the ground node, so we will set the voltage of this node to be as default V0. Why would we do this is because, as I mentioned before, a voltage is the potential difference. So if you, for example, say the ground plane is the zero plane, if we're looking at the gravitational scenario, then anything above that would have some potential. Obviously, you could dig a hole and then set that as being the ground level, and so now you have a different 0 point. So it doesn't really matter what I'm trying to say, and we will get there soon. So let's have a look at this circuit here, and obviously what we have here is we can first determine how many nodes are present in this circuit. To start with, we have a node that is present here because we're going across this branch, so that's node number 1. As we go across these two branches, we will get node number 2, and then we have a third node that is down here. Now, we could set either this node or this node or this node to be the reference node or the ground node. However, what we notice is that basically this is the node that is shared amongst a lot of elements here, and so we would select this to be the ground node. And as I said, you don't need to do this, but that's what we will select to be. We assign a voltage of 0 to this, and we will label these two nodes as V1 and V2. We see that this is placed on the resistors, but it doesn't really matter. This is V1 and this is V2, and we will proceed from there. Now, if we actually write down the set of equations that are pertaining to these nodes, what we have is that at node number 1, we can determine the currents that are flowing. So basically, at node number 1, we have a current I1, and we know what I1 is because it's an independent current source. And also I2, we know what it is. It's an independent current source. Why don't we give it values? It's just for generality. We are leaving it as capital I1 and capital I2. So let's look at node number 1. We will label the currents. And again, you can label these in any direction you would like to, and it will still work fine. However, you have to stay consistent. So for example, we are going to set I1 to be in this direction just because we expect the voltage here to be higher and we expect it, the current to flow through the resistor. So we set the I1 in this direction. We set I2 in this direction. We know what current is coming through here, which is I1, and we know what current is flowing through there, which is I2. Now, as we arrive at this node to try to label the current, we have to be very careful to remember that I2 is coming this way, the capital I2. However, this I2 that we placed here, this carries through this branch and arrives here. So we don't need to relabel this one as a different I. It's actually going to stay as I2. And we do need a new current label here, which is I3, because the I2 that comes here is added with this I2 to arrive at a different I, so that's labeled as I3. If we write the KCL at each one of these nodes, what we have is I1 is equal to I2 capital plus I2 small plus I1. At node number 2, what we have is capital I2 plus small I2 are equal to I3. So we have those set of equations, and what we need to do now is to solve those set of equations. So for that, we will resort to first denoting or writing what I1, I2, and I3, the unknowns here, because we know what capital I1 and capital I2 are. We write the unknowns I1, I2, and I3 in terms of the voltages at each node. And we use the passive sign convention, which we're saying is that every I is equal to the higher voltage minus the lower voltage divided by R. We're assuming that V1 and V2 are higher than the zero voltage. That doesn't matter as long as we stay consistent throughout the whole analysis. So I1 is given by V1 minus the voltage as the ground node, which is 0, divided by R1. That's what V1 is. I2 is V1 minus V2 divided by R2. And I3 is equal to V2 minus the ground plane voltage, which is 0, divided by R3. So now we can go back to the equations I mentioned before and plug in what I1, I2, and I3 are. So we had before that at node number 1, I1 capital is equal to I2 plus I1 small plus I2 small. But we know I1 small is V1 divided by R1. And we know I2 small is V1 minus V2 divided by R2. We know them from here. We plug in those equations. And we then arrive at the second equation, which is I2 capital plus I2 small is equal to I3. Well, I2 is a known factor. And then we know what I2 is, which is V1 minus V2 divided by R2. You have to remember, because you labeled I2 to be in this direction, you have to maintain that same sign convention that you use for I2. I see a lot of times students making a mistake here and now going V2 minus V1 divided by R2. But you have to maintain the same direction that you used for node number 1 in node number 2, because that current must flow in that branch. And finally, I3 is equal to V2 divided by R3. So now we have two equations and two unknowns, V1 and V2. If we solve for V1 and V2, we can find all the I's also. So now we've been able to find all the currents and voltages within the circuit. So we will solve some problems in class, obviously, but there are special circumstances or one special case that comes up that we need to deal with. So depending on what nodes the source is connected to, the approach varies. So if we have a voltage source that shows up between two nodes, we need to do something about that. You may ask why. The problem is the whole analysis that we're working on, which is nodal analysis, based on determining what are the currents that are moving through the nodes. However, we don't know what current is actually flowing through the voltage source. It's not a known fact. And so we cannot deal with that very well. So what we will do is there are two circumstances that are appearing here. So let's have a look at the circuit over here. We have node number 1, node number 2, and node number 3, and finally node number 4. We labeled node number 4 to be the ground node just for the ease, and we denote the voltage for that to be 0. So now we have 3 unknowns, which is V1, V2, and V3 that we need to solve for. Here, what we'll end up doing is that we have a problem because there's a voltage source between node V1 and the ground node. There's also a voltage source between the V2 and V3, the two nodes there. So there are 2 voltage sources that are appearing between the nodes. So this is the special case that we have to deal with. Now, if the voltage source is appearing between a node and the ground node, then it's very straightforward. What we will do is we set V1 to be at 10 volts because that's exactly what it is. However, if we have a voltage source that appears between 2 nodes where one of them is not a ground node, then what we have to do is to form a supernode. The way we would form a supernode is to remove the voltage source and just assume that this is only one node. So basically put a short circuit between it and deal with it as a single node. So let's go to the next lecture and next slide and deal with this. So whenever we have a voltage source that is connected between 2 nodes, we will replace it and any other element that is connected in parallel with it with a short circuit, and then we deal with that as a node. So in this case, we don't have any element that is in parallel with this, so we just have to put a short circuit between V2 and V3, and then we can write down the currents and voltages. So we know V1 is equal to 10, and the supernode voltage that we have here will give us the current the KCL equation. I1 plus I4 is equal to I2 plus I3. So the currents coming to the node, the supernode, are equal to the currents leaving the supernode. So in this case, what we have is I1 plus I4 is equal to I2 plus I3. What we can do at this point is to actually write down what I1, I4, I2, and I3 are. I1 is V1 minus V2 divided by the resistance. I4 is V1 minus V3 divided by the resistance. And I2 is V2 minus 0 divided by the resistance. And finally, I3 is equal to V3 minus 0 divided by the resistance. So now that we have one equation and one unknown, we have one equation and 2 unknowns, we need another set of another equation to be able to solve for the unknowns. Obviously, V1 is known because, as we mentioned before, we set V1 to be 10 volts. So it's V2 and V3 that are unknowns that we need to solve for. So in this case, we need another equation, and we utilize KVL around the loop that consists of the supernode. So in this case, we will remove all the other circuit elements. We don't need to necessarily, but just to redraw it and make it simpler for you, I have done so. And so now we have this loop over here, which consists of V2, V3, and the voltage source. Again, you don't need to remove the resistors or anything because you know that this is V2 and you know this is V3. So based on the current directions that we had selected, that we know this side must be positive, this side must be negative, and we also, again, because of the reference current direction we had selected, we know this must be positive and this must be negative. We do a loop here, which will give us the equation that minus V2 plus 5 volts plus V3 is equal to 0. Now we have 2 equations and 2 unknowns, and we can easily solve for the unknowns. We will then solve some problems in class to more clearly outline this.